Hello everyone, welcome to today's lecture. Before taking a dive into today's lecture, let us have a quick recap of what we discussed in the previous lecture. Right, so we were discussing about the instance-based learning, and in that we discussed about the basic understanding of instance-based learning. What is instance-based learning? The K nearest neighbor algorithm. K nearest neighbor algorithm. We took an example. We also saw the lab experiment with respect to this K nearest neighbor algorithm and the locally weighted regression algorithm as well, right? So these two algorithms, which are important from the instance-based learning approach, is what we have discussed so far. So in the today's lecture, we are going to take up two topics, that is the radial basis function and the case-based reasoning, right? So without any further ado, let's start the radial basis function first, right? So the radial basis function, this is actually one of the approach to the function approximation, right? And as it is mentioned that this is closely related to the distance weighted regression, right? This type of approach, uh, this approach to the function approximation is closely related to the distance weighted regression, but eager instead of lazy. So it's a eager learning instead of the lazy learning approach, right? So as you can see here, that it is the global approximation to target function, right? So you might recall and say me that, sir, as we discussed in the initial introduction sessions of our instance-based learning, right? So we discussed there that this instance-based approaches, they are actually, they can construct the different approximation to the target function, right? And it this instance-based learning, they basically construct an approximation which are typically designed to perform well over the entire instance space, right? So, and we also discussed that this particular instance-based learning methods, right? For example, this a nearest neighbor and the locally weighted regression. They are basically straightforward approaches to approximating those real valued or discrete value target function, right? So, how is this global approximation to the target function, right? We can say that it is global approximation by in the terms that it is the linear combination of all the local approximations, right? It's the linear combination of the local approximation. So where these type of approaches can be used, these radial basis functions can be used, right? So one such use case is the image classification, right? So you must have came across some machine learning projects, some projects which deals with taking a image from a still camera or you know a moving camera also for that matter, and taking the image and classifying those images as what type of object that it belongs to, right? Whether it is an animal, it's an object like a car, or it's is it a human, and so on, right? So basically, image classification is one of such use case for this radial basis function networks, right? So it's a kind of a neural network itself. So talking more about it, as you can see here, this is the radial basis functions network, right? Right here, right? So we, since we have discussed about the neural network earlier, right? So it will be easier for you to understand that this particular network is also, a multi-layered network. So we have different layers here. We have input layer, we have a hidden layer, and then we have output layer, right? So this particular you know is a representation of a radial basis function network. So in this hidden layer, typically in this particular hidden layer right here, right, this in this hidden layer, each hidden unit, right, like these are the hidden units right here. So each hidden unit, it produces an activation. Now activation, how is it determined? This particular activation is determined using the Gaussian function, right? Hope you remember the Gaussian kernel functions that we have set up for this. So this activation is basically determined by the Gaussian function. Now these Gaussian functions are basically centered at some instances. Let's say xu, right? Let's name it like xu. These Gaussian functions are centered at instances, let's say xu. So we can say that its activation will be close to the zero unless the input is near to xu, right? So if the if its activation will be, it will be close to zero unless the input x is near to this xu. Near to this xu means the value of xu, if it is close to the value of input x, then we can have the activation, we can say that the activation will be nearly zero. So the output unit here, as you can see that this output unit, it produces a linear combination of these hidden units, right? It produces the linear combination of this hidden unit activations, we can say. So this network here, it shows that it has, just one output, but we can have other networks wherein we can have multiple output units as well, right? So this particular example is with respect to only one output unit, but we can have multiple output unit. Right now, this input here, like a1 of x and a2 of x, so on till an of x, these are basically the attributes which describe those instances, right? So instances are x. So you can say this ai of x, they are the attributes describing these each instance right here. Okay. So when we need to have the linear combination, we can say that the learned hypothesis is a function in the form of this, right? The learned hypothesis can be of the form of this. So this is basically what we are trying to do. We are trying to we are trying to sum up all the products of weight as well as the kernel function right here, and the added weight, right? The initial weight that we are trying to add. Right. So one common choice for this kernel function right here is using this formula, right? So this is the defined formula. You can say that it is centered at the point xu with some variance. You can say variance, that is uh, mu. Let me draw it. Mu u square, right? So this is the some variance that we are trying to put here. So moving further, now the training, how do we have this radial basis function networks training, right? So the question that comes is like, what XU to use, right? What XU to use for each kernel function ku d of xu comma x, right? So the answer for is that scatter uniform throughout the instance space, right? Should have a scattered uniform throughout the instance space, or use training instances which reflects the instance distribution, right? Another important question that arise here, that is how to train the weights, right? How to train those weights? We need to assure here that Gaussian is kernel U, that is Ku. So the first step that we can take to train those weights is to first choose the variance, like I just mentioned here, right? This mu u square. So the first is to choose the variance, and variance is perhaps nothing but it is the mean value, right? The mean for each ku. The example for it is that the exponential mean, right? So the second step is to then hold the ku fixed and then train the linear output layer, right? We need to fix the value for the kernel ku, and then we can train the linear output layer, which is efficient method to fit the linear functions, we can say, right? So these are the two important questions that arise in front of us, and we can say that these are the the approaches. If we follow these approaches, we can have the answer for. We can answer these things, right? So let me uh, let me demonstrate you one more thing. Yeah. So the case-based reasoning. The second part is that is the case-based reasoning, right? So in the case-based reasoning, we can in the case-based reasoning, we can apply the instance based learning even when the x is not equal to the Rn. Rn is nothing but the number of the real numbers here, right? The set of real numbers. So we can say that the we can apply the instance-based learning even when the number of instances is not equal to the real number. So what is the requirement here? What is that will be needed here? The important thing is that we need different distance metric, right? We have learned about different distance metric from the in the previous lecture as well. So hopefully you remember those aspects. So we need to take care that we need to have a different distance metric here. Now the case based reasoning is instance based learning, of course, right? And it is the instance based learning applied to the instances with symbolic logic descriptions, right? They are applied on the instances with symbolic logic descriptions. So this is just an example of what do we mean by that. This is just an example taken. So when we talk about those case based reasoning in cadet, now what is this cadet? So cadet, you can say that it is, for example, let's say in cadet we have 75 stored examples for mechanical devices, right? We have, let's say, 75 stored examples for of mechanical devices, right here. So each training example, right? Each of the training example, let's say qualitative function and the mechanical structure, right? Each training example will have a qualitative function and a mechanical structure. So what is the new query for this particular cadet based reasoning? And the new query is nothing but the desired function itself, right? The desired function that we are trying to look forward here. And what is the target value in that case then? The target value will be the mechanical structure for this particular desired function, right? The mechanical structure for this desired function will be our target value. Now, now the distance matrix, like I said, the distance matrix is nothing but we have to match the qualitative function descriptions, right? So with this understanding of case-based reasoning and cadet, let me take an example. Let's have a case scenario. Like let's have a stored case and a new problem which is coming, right? So let's say we have a stored case with we can say T junction pipe, right? A stored case and a problem specific, a new problem which is for which the specification is given. So the stored case is the T junction pipe, right? This is our stored case, and as you can see, this is the structure for it, right? And we have the function associated with respect to the stored case, right? And then we have a problem specification that is water faucet, for which we have the function, right? That is nothing but our desired function, and we need to define the structure. What is the structure for? So that this particular top half of this figure, it describes a typical design uh, in case of the library of cadet, right? So by cadet, I mean that the cadet is basically the system which employs the case-based reasoning, right? It is the you can say that it is the system which employs this case-based reasoning. Also, in other words, is also called CBR. case-based reasoning. So in this function, right, this typically design this particular half segment, half of the diagram here. This describes the typical design fragment in case of in case library of cadet. So the function here is represented by the graph of the qualitative dependencies among this particular T junction, right? The T junction variables. Now, what are the variables here? As you can see, T stands for temperature, Q stands for the water flow, right? And as you can see, the flow of the diagram here, right? The temperature, there's some water flowing from here, also with some temperature of that water, and some water flowing here with some temperature there, right? So, and as you can see, it's a T junction, so the output that we are getting will be, you can say, a new temperature and a new uh, water flow here, right? So the function, as you can see on the right hand side of the figure, that the function for both the water flow as well as the temperature is the, you can say, the mixture or the summation of the water flow from the both the sides, that is q1 and q2, right? And the new function is q3. The new output that we got here is q3. Similarly, the temperature that we will be getting, that is T3, is nothing but the summation of the temperature first, that is T1, and the second temperature, that is T2. So you can assume your own example, that is, if the T1 is hot and T2 is also hot, that means that T1 is high and T2 is also high, temperature is high, then T3 will definitely be higher, right? The temperature is going to be high. But in case if any of the two, that is T1 or T2, any of them is slightly low, then the output will also be considerably, it will be low, right? That is, let's say if T1 temperature is low and T2 is high, the summation of these two will be the T3, right? So this is the first half, or you can say the upper half of this particular diagram here, right? Now the bottom half of this figure, this is typically the typical design of a problem, right? As I mentioned, it is typically the problem. So we have the function for it, and we need to define the structure, right? So this can be the example of what we can say, that is case-based reasoning, right? So, like I mentioned here, in the instances represented by rich structural descriptions, right? It is represented by rich structural descriptions. Now, multiple cases retrieved to form solution to the new problem, of course, right? Multiple cases, when it can be combined cases also. And we can say that the tight coupling between the case retrieval and problem solving, right? The tight coupling between the case retrieval and the problem solving. So at the end, we can say that the bottom line is that the simple matching of the cases useful for the task, such as answering help desk queries. Now, what do we mean by help desk queries? Right. So help desk queries. Why? Because it depends. The answer to this, or the solution to this, depends on the query. Right. Depends on particular case. So it is based on a particular case. So depending on that case, the answer will be formed. So simple matching of cases useful for tasks such as answering help desk queries. And the other area are still on ongoing research, as it is mentioned here. Right. So that's all about the case-based reasoning in this particular, we can say cadet, that, and cadet is basically the system which employs the case-based reasoning. Right. So that will be all for today's lecture. We shall meet in the next lecture with taking up the new topic. Right. So we shall conclude the lecture here. Thank you.